Alright, I want to talk about continuity. What does it mean for a function to really be continuous? We really want to nail this thing down and define it in terms that we talk about in the calculus class. Now I know that in algebra, when you say that a function is continuous, you say that it's continuous if you can draw it without having to lift your pencil. And that's a pretty good definition, but it's not really too rigorous. We want something that's a little more mathematically precise. So we talk about continuity in the context of limits. This function here has three discontinuities, and I'd like to talk about what exactly it is that makes them discontinuous. So one function, it's discontinuous here. The reason that it's discontinuous is because if we call this the value of x, we would say that f of this x value does not exist. Okay, if this value is a, we would say f of a does not exist. And that's fancy talk for just saying that there's no point there. All right, saying, there's no point corresponding with x equaling whatever this x value is. So there's no point there, f of a does not exist. In this case, it's still a discontinuity. You can lift up your pencil. But what makes it so? Well, it satisfies the condition that this one did not, right? F of this number, whatever this x value is here, f of a, call it a, f of a is this. So f of a exists, but it's a discontinuous function because the limit does not exist as x approaches a, right? The limit from the left equals whatever this y value is. The limit from the right equals whatever this y value is. Saying those aren't the same number, so the limit as x approaches a does not exist. And that's what destroys continuity there. And this last one here, this satisfies both of the criteria that the other two did not. F of a exists, right? F of this x value exists, it's here. And the limit exists. The limit as x approaches a is this number, but they're not the same. They're not the same y value. So in this case, f of a does not equal the limit as x approaches a. And that gives us the three circumstances under which a function will be discontinuous at an x value. And so we have three conditions that need to be met in order for a function to be continuous at an x value. For continuity at an x value, x equals a, three conditions must be met. The first one is f of a must exist. In other words, there's got to be some point there, right? F of a must be at least defined if the function is going to be continuous. The second condition is that the limit as x approaches a must exist. At the very least, if the limit does not exist as x approaches that number, if the function from either side isn't going to the same value, then the function is going to be discontinuous at that x value. And the third condition is that the limit as x approaches a of the function must equal f of a. I abbreviate that by saying that these two answers must be the same number, right? That's like this one here. The limit exists and the function exists, but they're not the same number. If you fill this dot in, right, which is the case at every other point, it's implied, at every other point along this curve, then and only then you have continuity at that point. So you need to know these three conditions for continuity at a point, and no single one. If it's just these two, if you know exactly one of these two is true, but not necessarily the other, you cannot assume that the function is continuous. So these are the three conditions. You have to know them, and let's do a couple of examples. The first thing you got to know how to do is know how to spot a discontinuity pretty much just from looking at a function. The basic rule is if it's not some goofy looking piecewise function, if it's just one f of x, it's just like a single expression like these 6 examples, pretty much all that you got to do is look for, if you want to spot a discontinuity, you just have to look for division by 0. Anywhere where a function has division by 0 automatically is going to be a point of discontinuity. So just from looking at this, I'm asking where are these functions? These functions all have discontinuities. Where are they discontinuous? This thing is discontinuous at x is 1. It's got a vertical asymptote. Forget about it. So you would just say discontinuous at x is 1. Again, same thing. Any values that are going to cause division by 0 are automatically going to be points of discontinuity. So where is this thing discontinuous? At x equals plus and minus 2 with factors 4 plus x, 4 minus x. Where is this discontinuous? Even though it's x plus 1 over x plus 1, I still can't plug in x equals negative 1. Right? This function equals 1, but only if x does not equal negative 1. So negative 1 is a point of discontinuity. So x equals negative 1. For that, come down here. The exponential is fine, but you can plug anything into it, but you still can't divide by 0. So this function is going to have a discontinuity at x equals 0. This function is discontinuous also when x equals 0. Every other point is fine, but you still can't plug in 0 because it causes division by 0. And lastly, cosine x. Cosine x has a lot of zeros. You want to know where is cosine x equal to 0? And the answers are, say, if you know your trig, pi over 2 plus n pi, right? Those are the angles that terminate either straight up or straight down. So infinitely many discontinuities, it's the secant function. So just from looking at it, you got to know how to spot a discontinuity. You can pretty much automatically say a function is discontinuous wherever division by 0 would occur. Let's do a piecewise example. Here's f of x. It's piecewise defined. It's a parabola if x is less than or equal to minus 1, and it's a line if x is greater than a minus 1. The question is, does this function have any discontinuities, and if so, where are they? Well, for this piece by itself, it's just a parabola, no denominators. Everyone's familiar with what a parabola is. It's nice and connected. Definitely this thing by itself doesn't have any discontinuities. Neither does this. It's just a straight line, totally connected anywhere, no problem. When you get a piecewise function, usually the only points of contention, the only ones that are up in the air, is the breakpoints, right? So this function stops acting like x squared plus 1 at the value of x minus 1, and then it starts being a line at the same value. So it's one thing up until minus 1, and then it's something else after that. Question is, do these pieces line up? Do they meet each other at the point x is a minus 1? We'll look at it algebraically and then graphically. So I'm looking at this thing. The only point that's up in the air is x is negative 1. So what you have to do is you have to be sure that the three conditions are satisfied for continuity. So that's, does f of negative 1 exist? And yes, it does. I can plug in minus 1 is here. F of negative 1 is 2. No problem. Then you have to determine whether the limit as x approaches negative 1 exists. And if so, does it equal the answer that we got for plugging minus 1 in? Does it equal 2? Let's find out. We take the limit as x approaches negative 1 from the left. As x approaches negative 1 from the left, the function is acting like this. All right? So basically all we have to do is plug minus 1 in and see what the answer is. So as x approaches minus 1 for this function from the left, we use this piece because x being less than minus 1 falls into this conditional. So plug it in and you just get 2. And then you have to compare that to the limit as x approaches negative 1 from the right. That's x is greater than minus 1, so that's in this conditional. And since this is a nice, easy, well-defined function to figure out this limit coming from the right, all you basically have to do is plug minus 1 into this bottom piece. And when you plug it in, you get that limit is 4, right? Just plug it in. And so from the left it's approaching 2, from the right it's approaching 4, and so the limit as x approaches -1 does not exist. So it fails to satisfy that second condition. So therefore this function is discontinuous when x is -1. To show you what that looks like, so here's the graph. Here's -1, and here is 2. The function x squared plus 1 looks like this. It's the parabola x squared shifted up 1 unit, and it only acts like that if x is less than -1. So I started drawing it here, but I really should have went here. There's a dot there. So that's the portion of the graph that's a parabola. And the other piece is x plus 5. Now, x plus 5 has a y-intercept of 5, so that's 2, 3, 4, 5, and it has a slope of 1. So it looks like that, and it's going down to 4 right there. So here's the graphical version of what we just did. Let me get that out of there. All right. 1, 1, 2. From the left, the function approaches 2. This is supposed to be a parabola. I don't know how well that's showing up, but it's the parabola from the left, and from the right, it's the line. Here's the open, right? It's not defined there, but it's going to a value of 4 from the left, 2 from the right. There's the jump discontinuity. The limit does not exist. But if I change this up, if I switch the function from x plus 5 to, say, x plus 3, then we'll be in business. So now, if we start all over again, and again, the only point of contention is whether it's continuous at x is -1 or not. So we go to compute the left and right-handed limits. The limit from the left, same thing. You're going to use this old piece, plug -1 in here, you still get 2. Compute the limit from the right, plug -1 in here, and you get a value of 2 instead of the old 4. Now, these two match up. And so the limit as x approaches -1 now does exist. And it does equal f of -1, which was 2. Effectively, it takes this part of the graph and adding 3 to it, right, it bumps everything down by 2. And so what used to be that is now this. And now these pieces match up. And so this function is continuous when x equals -1, because both of the pieces from either side of -1 line up. The limit exists, and it equals the value of the function at that point. I got another example here that asks for find all the discontinuities of this, if any, and determine the value of b, the constant b, that will make this function, if possible, continuous when x equals 1. So you look at the individual pieces, try to find any discontinuities in them. 1 over x plus b. You're looking at this and say, okay, this is clearly discontinuous when x equals 0. But 0 is not in the conditional, right? So the value, the graph of the function is going to look like 1 over x plus a constant, but only if x equals, only if x is greater than or equal to 1. This would have a discontinuity at 0, but 0 is not in the conditional, so this piece doesn't have any discontinuities. And this is just a line, so that's not a problem. This doesn't have any discontinuities, so the only point that's in question is at x equals 1. Is it possible to make b such that the two pieces join when x is 1? So you evaluate f of 1. To make sure that it exists, and it does, you just plug it in here and you get 1 plus b. So whatever b is, f of 1 does exist. It's going to be 1, it's just going to be 1 plus b. And then, like the last example, you need to compute the limits as x approaches 1 from the left and compare that to the limit as x approaches 1 from the right. F of x goes to 1 from the right. And as x approaches 1 from the left, you're using this conditional because we're saying that x is less than 1. And as x approaches 1, you just plug 1 in, and you get b plus 3. Right, plug in 1 for x, and you're left with whatever b is, plus 3. And the limit is that as x approaches 1 from the right, x is greater than 1. You go to the other conditional, plug in 1, and you get 1 plus b. So, from either side, if the function is to be continuous when x equals 1, then this has to equal this. So you set them equal to each other and see what happens. You say b plus 3 has to equal b 1 plus b plus 1. And if this equation has a solution, then that's the value of b that makes it continuous. But immediately we see that the only way for this to work out is if we subtract b from both sides, we're left with 3 equals 1, which cannot happen. So there is no value of b that makes this statement true. So there's no value of b that can make the left and right-handed limits be the same number. Therefore, there is no value of b that makes that could possibly make this function continuous. But just like the last time, if I come in and change something, if I change this function from an x plus b to an x minus b, then we'll see that the thing is going to have an answer. So same thing, determine the value of b that makes this function continuous. First, make sure that f of 1 exists. And it does, plug it in, and instead you'll get f of 1 is 1 minus b. And then you go to evaluate the limits. The left-handed limit is still going to be b plus 3. But the right-handed limit now is going to be 1 minus b. So, and then to determine whether this is going to work out, you set these again equal to each other. So you get b plus 3 must equal 1 minus b. And then you go to solve the equation and bring b over to the other side. So you get 2b equals, when you bring the 3 over to the other side, 1 minus 3 is minus 2. So then you divide by 2 and you get b equals minus 1. And you can see that this one is going to work out. If b equals minus 1, then the two pieces are going to line up. The limits are going to be the same number, and hence the function will then be continuous when x equals 1. Moreover, if b is minus 1, we can go and plug that value back into all the numbers. If b is minus 1, then f of 1 is 1 minus minus 1, which is 1 plus 1, which is 2. So the limit from both sides as x approaches 1 would be 2, and that's what's going to make these two pieces line up, and that's the value of b that would make this function continuous everywhere. The last thing I want to talk about is types of discontinuities. There are two different types of discontinuities. One is removable, and the other is non-removable. From looking at a graph, we call a discontinuity removable if it's just a puncture, if it's one of these two types of discontinuities, right? So if you could remove the discontinuity by placing a point where the hole is, right? Only if it's a puncture. So this is a removable type of discontinuity. These two types, removable, because they're hole types. Whether there's a point here or not, regardless, we call it removable. Unlike these, which are non-removable, so non-removable. So removable and non-removable discontinuities. Can you guess what the condition is for calling a discontinuity removable or non? It's whether the limit exists, right? The way to call a discontinuity removable is to say that the limit as x approaches the x value exists, right? In both of these cases, the limit exists, the limit exists, and that's what makes it removable. Over here, since the limit does not exist, we have an asymptote type discontinuity here, and the limit does not exist here. It's a jump. We call these non-removable because the limit as x approaches that number does not exist. Sometimes these are referred to as jump. This is a jump discontinuity, and sometimes this is called an asymptote discontinuity. But basically, if it's a whole, the limit exists, and we call that a removable discontinuity. So what are some functions that have removable discontinuities? Well, two examples come to mind. One of them is this one, right? This has a discontinuity at the value x equals -1. You can't plug in -1, you get division by 0. However, when you factor the top, you get x plus 1, x minus 1, and the common factor divides out, of course, and it's what you're left with is a whole in this function. So whenever you have a factor and cancel type of limit, or factor and cancel type of situation within a problem, that's a sign of a removable discontinuity. Because if I asked, what is the limit as x approaches -1 of this, you could evaluate it by factoring and canceling. Right? You factor, cancel, plug the bad value -1 into here, and get that the limit equals -2. So because the limit exists, this function has a removable discontinuity at x equals -1. Same thing goes for sine x over x. The special trig limit as x approaches 0, the limit as x approaches 0 of this does exist, and it's 1. So it has a punctured discontinuity at the point when x equals 1. This is another removable discontinuity function. This thing, however, has a non-removable discontinuity at x equals 0. Really quickly, if you evaluate the limit from the right, you drop the absolute value bars and you get 1 over 1. So the limit from the right, I'll just draw it in quick, is equal to 1. But the limit as x approaches 0 from the left is equal to -1. So the graph of this kind of meets like this. The pieces don't meet up. The left and right-handed limits for this function do not agree. And hence, this is a non-removable discontinuity at 0. So let's check this one out. Last one. The point of contention is x equals 0. And even though f of 0 is defined, right, f of 0 or y of 0 is 1 by definition. If we take the left and right-handed limits, maybe it's not going to work out. As x approaches 0 from the right, the limit is 1. So the limit from the right, the limit is, the y value is 1 because it's always just 1, right? However, as x approaches 0 from the left, you use this one, because negative numbers are in this conditional, and as x approaches 0 from the left, for this one, it goes to -infinity. So that one shoots down to -infinity, and anything that has infinity or -infinity in it does not exist automatically, and so this discontinuity at 0 is a non-removable discontinuity. One theorem that deals with continuity is called the intermediate value theorem. Loosely speaking, it says that if a function f of x is continuous, if it's continuous on a closed interval a to b, so let me draw one such function. Doesn't matter how I draw it, I won't get too fancy, but it says that if the function is continuous from a to b, then for every y value between f of a and f of b, all right, call that k, say, for every value between these two y values, there is going to correspond an x value somewhere between a and b, such that f of x equals k. So let me just state that again. It really states the geometrically obvious. It says that if this function is continuous, nice and connected, then every point between the endpoints, between the f of the endpoints, gets mapped onto by something. So if this value here is, say, a y value of 1, and this value is 10, it basically says that the function hits all values between 1 and 10, and that there's always going to be some x value between these two that's going to map onto all of those numbers. So for example, sticking with this 1 and 10 example, if you know that it's continuous, and you know that f of a is 1, and you know that f of b is 10, and you have a is less than b, then you're guaranteed that the equation f of x equals, say, 6 is going to have a solution somewhere inside A and B. Probably a better example of that is if a function is continuous and you know that f of A is some positive number and you know that f of B is a negative number, then you can say that because of the intermediate value theorem, between A and B, the function must have at least one 0, right? Because 0 is intermediate to this positive number and this negative number. And of course, it'll also work if you reverse roles. Of course, if f of A is negative and f of B is positive, there's going to be at least one value where the function value is going to be 0. This has a couple of cool results, actually. Even though it is geometrically obvious, it does have a couple of neat consequences. But just to be sure, it does only work if the function is continuous. Because if it's discontinuous, anything goes. You could have a function, if here's A and here's B, and you know that f of A is up here, but f of B is down here. If the function is discontinuous, it could be shaped like this, right? And there's no guarantee that it's going to have a 0 value. So this might just seem like a little nitpicky thing, but it's in the general calculus sequence, so you just have to know about it. But it does have some cool results, which I'll talk about now. One thing that I thought was pretty cool was that any shape that you can think of can be contained in a square, in a tangent square. And let me show you what I mean by that. If you draw any closed loop and draw a rectangle around it that's tangent to the figure at all 4 of the rectangle sides, okay? Imagine me taking this shape here, the shape, and rotating it, but keeping these sides of the rectangle parallel, right? So that as I rotate this, the rectangle stays, it makes an adjustment on the fly, so that when it's in, say, right, that's supposed to be an approximation of the same figure, so that when it reaches here, the rectangle like changes, and it looks like that, right? So as I rotate this, the bounding box of the rectangle changes to adjust for the shape of the figure. According to the intermediate value theorem, I believe, you can contain any figure in a square, in a perfect square, right? Like this is long like that, but if you rotate it just right, it'll come out to be contained exactly inside a square. And this is my reasoning for that. Let's say that you have it just like this. Call this length here. And no matter what figure you draw, you can definitely contain it in some non-square rectangle. So let's say that you draw some goofy looking figure, and we'll call that DH for distance horizontal. And we'll call this dimension dV for distance vertical. Now, clearly these two things are not the same. Now let's say that this is an angle of 0 degrees, right? 0 degrees. dV is a lesser value, dH is a greater value. Now imagine what happens as I rotate this figure 90 degrees. I take it and I rotate it by 90 degrees. dV and dH exchange places, right? dH is going to shrink down and be what the size of dV is now. And dV is going to expand to be the size of dH after I go through and turn this thing 90 degrees. And so, if we say, let's see, this one was dV, this one is dH. And so by the time I reach 90 degrees, dV is going to be what dH was. So it's going to get there somehow. And dH is going to be where dV was, and it's got to get there somehow. And so there must be some spot by the intermediate value theorem, if you believe that these functions are continuous as you rotate this figure, if they're nice and connected. If they are indeed nice and connected like that, then by the intermediate value theorem, there's going to be some spot where dv and dh are the same size, and that's going to be the figure, that's going to be the case where it's exactly contained inside a square. Just a neat little application of the intermediate value theorem there. That's it. I think that's all I got. As long as you know what the intermediate value theorem is, and that it relies on continuity, and you know the definition of continuity, the three conditions, and you know how to spot a discontinuity from looking at a function. You look for 0 in the denominator, and you can distinguish between a removable and non-removable discontinuity. You're in pretty good shape.